Hey guys, I just wanted to, with me not being in class tomorrow, I wanted to give you some information so that you can at least work on some practice while you're in there. And this first part is going to be kind of an extension of what we were doing in class with molar mass. And before, when we were doing it, these were the practice problems we ended class with. We were talking about individual elements, right? Bromine, and we can look on the periodic table and find the molar mass of bromine, and same thing for nitrogen. But what happens when we have compounds, okay? So before we talk about molar mass, let's just talk about moles in thinking about our compounds, okay? So I'm going to be looking at this first one here where it says 1 molecule of H2O. Hopefully we are okay with the statement that 1 molecule of H2O has 2 atoms of hydrogen and 1 atom of oxygen, and that comes from looking at the formula, right? The formula tells us the ratio of atoms that we have. What it also tells us is how many moles of those atoms we have. So remember, when we're looking at this, a mole is just a number, right? 6.022 times 10 to the 24. But when I talk about moles, I'm just talking about how many of those things I have, just as if we talked about dozen. So before we get to this next statement, I want to just talk about, and hopefully we understand, that if I have a dozen H2O molecules, that means, right, our ratio is 2 to 1. Right, of hydrogen to oxygen. So if I have a dozen hydrogen molecules, that means we're going to have 2 dozen hydrogen atoms. Just do H atoms. And 1 dozen oxygen atoms based on this 2 to 1 ratio. So the ratio always stays 2 to 1. So if I start talking about moles, right, again, that just means I have 6.022 times 10 to the 23rd of these water molecules. So if I have 1 mole of water, I have a 2 to 1 ratio of hydrogen to oxygen. I just now happen to have 2 to 1 mole ratio, right? So I have 2 moles of hydrogen and 1 mole of oxygen. So you can think of this like a bicycle, right? We have a bike frame. I'm not going to draw it because I'm a bad drawer. But if it's simply you have wheels and a bike frame for a bike, you have 2 wheels for every 1 bike frame. And when you put all 3 of those things together, you get 1 big bike. That's what's happening here. We need 2 hydrogens to attach to 1 oxygen, and those 3 things attached make 1 of our water molecules, right? So we got the big, right here is our big constructed, finished substance, and then these are the pieces that make it up, okay? So our chemical formula not only tells us our atomic ratio, but more importantly, it tells us our molar ratio, okay? And we'll come back to that in a second. But we can also talk about the molar mass of molecules, because if I have, right, 1 mole of water, then I have 2 moles of hydrogen and 1 mole of oxygen, which now, when I break it into its pieces, I can figure out, look at the periodic table, hydrogen has a molar mass of 1.01, but I have 2 moles of it, so I'm going to take that into account, which gives me, right, 2 times 1.01 grams per mole. So that means we have 2.01 grams of hydrogen, and then we have 1 mole of water, which is 16 grams per mole, and we would have 16.00 grams. So the molar mass here would be 18.02 grams per 1 mole of water, right? So that's how we're going to calculate molar mass. We just take the sum of all the atoms, right, the masses of all the atoms in the molecule and the compound. So I'm going to let you figure out the molar mass of oxygen and NaCl and talk a little bit about the calcium phosphate. So the formula is so important here because it's telling us how many of each thing we have. And when we're counting that in the mass of our car, I was doing the analogy in my head. We want to take into account the pieces of all of the things that make up this make up this compound. So thinking about our bike again, right? We have the bike frame and we have the bike wheels. And if I just took the mass of one wheel plus the bike frame, I would be missing a significant portion of our mass. Because if you're thinking about like aerodynamic bikes, they try to make the frames as light as possible. So the tires make up a good portion of that mass. So it's important that we have two tires in our bike when we're massing something. So when we're looking at calcium phosphate, we have 3 calciums. And when you're looking, we have parentheses here and a 2 on the outside. It means we have 2 phosphates. So we're going to have 2 phosphoruses and 2 times 4, or 8 oxygens. And that's important because I need to add up 3 molar masses of calcium, 2 times the molar mass of phosphorus, and 8 times the molar mass of oxygen in order to get that mass for calcium phosphate. If you don't take into account all of the pieces, then you're not going to have the correct mass. And if you don't have the correct mass, you're not going to be able to get the correct answers. So we're going to do the calcium plus the phosphorus, 2 times that, 30.97, plus 8 times oxygen. This is going to have a total molar mass, 310.18 grams per mole of that substance. Okay, you can do the other 2 as practice. So now that we can calculate molar mass of substances, other than just regular elements, we can go back and do more problems like we were doing before. We were converting from mass of our substance to grams, our mass to moles, or moles to particles. So these first 2, or this first one, is a one step. Remember, we have Avogadro's number as a conversion factor, which is allowing us to go from between moles and particles. And we have molar mass, which allows us to go from between moles and grams from the periodic table. Okay, so this first one is a single step. I'm not going to do it. You can do that for practice and you can check your answer. But how many total atoms are in 5.32 grams of KOH? Okay, so we're going to start with what we know. We have this many grams of KOH, and I know that I'm going to try to convert away from that. And the only conversion factor that we have available to us is the that involves grams, right? So I'm thinking about my puzzle pieces. I know that I have grams and I want to get rid of grams. The only conversion factor that has grams is molar mass. So that's my first place to start. I'm going to use the molar mass of KOH, which is a potassium plus oxygen plus hydrogen, and I get 56.11 grams, right? So that's good. I cancel out my grams of KOH. Now, we want to get to total atoms in KOH. And I can go we want to get to particles. And if I'm thinking here that we can get rid of moles of KOH, and my other conversion factor, we're not going to use molar mass again. We just converted away from grams, so we're not going to convert back to grams. So the next conversion factor I could use is Avogadro's number, right? A's number of KOH. Right, in 1 mole, there's that. Now, this is where it becomes important for you to understand what do we call KOH in its smallest pieces. I agree that there are atoms and there are ions in here, but if I'm talking about KOH, that is an ionic compound, and the smallest piece of an ionic compound is a formula unit. Right? So I can't just say atoms and call it a day, because that's not true. All of the conversion factors we use must be true. So I go to formula units. And we have one extra step in order to get to total atoms, because now, right, remember Avogadro's number is just a number, so my unit that we have is formula units of KOH. And in one individual formula unit of KOH, there is actually 3 atoms in that. You have a potassium, you have an oxygen, you have a hydrogen. So we're adding another conversion factor that we can use, and it's the formula, which allows you to move between compound and, I guess, smaller pieces, right? Or pieces. The total compound, the full compound. In this case, the full compound was KOH. And the pieces that make it up. And that's what we were doing there, because we had the compound of KOH, and we were trying to go to atoms. Oopsies. Okay. So we had that one extra step that you might not have seen, but again, when we're doing conversion factors, especially with this one, we need to make sure that it's true. I can't say 1 mole of KOH has Avogadro's number of atoms of KOH, because that's not how we talk about formula units. So if we do this, 23 times 3, I get 1 point, oopsies, I'm still on that. I get 1.71 with 3 significant figures times 10 to the 23 atoms. And technically we're talking about atoms of potassium, oxygen, and hydrogen, but we don't have to specify that. We just have that many atoms. So here there are more practice problems for you to do that are specifically talking about the compound, like here, how many carbon atoms are there in a sample of C2H6O. So you're going to have to use that formula as a conversion factor, and I'm going to let you guys figure that out in class together.